All right, so we're looking at this idea of the electromagnetic spectrum. Now, just the formula for the speed of light, there's two formulas. The formula that actually where you can work out the speed of light is given by this, mu 0 E 0, where mu and this epsilon over here are constants. We actually have those constants given to us in our formula booklet. We go to our formula booklet here. We have them over here. The permittivity of free space and the permeability of free space. It's equal to this. So this is looking at an electric field, forming an electric field, and this is looking at forming a magnetic field. And when we put it into here, we get C is about 3 times 10 to the 8 meters per second. Okay? And it depends purely on these two constants. Now, as you go into different materials, these things change. So when you go into, say, the glass, the permittivity and the permeability actually change. The ability to form an electric and a magnetic field changes. This is for free space. This is generally for a vacuum, and also for in air, we take it as that. And it gives us this value. So the speed of light is constant. We're going to be looking mainly at today when we're looking at things, we're going to be looking at C is equal to 3 times 10 to the 8 meters per second, or 300,000 kilometers per second. So if I go back to this diagram, I just pulled this up from the internet. This is an electromagnetic spectrum. It gives us our wavelength over here. This is our wavelength, and this is our frequency. Now, as we said, C is equal to F times lambda. So this times that gives us our speed. So obviously, if this is 3 times 10 to the 8, then as the one gets, as your these two, if you've got your frequency and your lambda, obviously as the frequency gets bigger, the wavelength would have to get smaller. There would be an inverse proportion relationship between them. All right? Frequency will equal 3 times 10 to the 8 over lambda. All right? Inverse proportion relationship. As the one doubles, the other will have to halve. All right, so as frequency gets bigger, wavelength, and correspondingly as the frequency gets smaller, the wavelength will get bigger. So when we look at these, now you can't really see this very well, I suppose, but when you look at these, you've got your very short wavelengths over here. These are short wavelengths, small wavelengths. These lead to high frequency. So these are your real high frequency. Okay. And also, what is interesting is that the frequency gives an indication of the energy of the wave. High frequency leads to high energy waves. And we're going to see this formula later on, that the energy of light is given by this formula, HF. The energy is proportional to the frequency. So if you've got very high frequency, you're going to have very high energy waves. And your high frequency waves are like your gamma rays and your X-rays. All right, these are high energy waves. Sorry? H is something called Planck's constant. We're going to when we do the quantum physics, we will look at Planck's constant, but it's a constant value. Very important constant that comes up all over in physics. Okay, so these high frequency waves here, these high frequency, very short wavelength, are your high energy waves, your gamma rays, and these come from radioactive materials and so forth. They give out these gamma rays. These things can cause a lot of damage to a person if you get exposed to gamma rays and your X-rays. So that's why when you go for an X-ray, the person giving you the X-ray will go and hide behind some protective screen so they don't get X-rayed all the time, because they're using those machines. In hospitals, they will have certain discs on them that will measure or pick up the amount of radiation they're exposed to, so that they don't get exposed to too much. But these gamma rays, they come from radioactive material. your X-rays. This comes from usually using tungsten, firing electrons at tungsten. And then we go down, and as your wavelength over here, your wavelength is increasing there. Obviously, your frequency is decreasing. Your energy of your waves decrease. And you go right the way to the other side, and where we look at our radio waves and our microwaves. These are radio waves, microwaves, all our communication that we have generally. We have our microwave towers, cell phones, mobile phones, and so forth. These are your long waves. And you get here, some are even up to 10 to the 3 meters. And they are comparatively, the frequency gets comparatively small. But just to give you an indication, let's just take our visible light. This is our visible. So our eyes pick up just a very small range. The visible range. It's a good range to pick up because a lot of light, like for instance light that comes from the sun, is in that visible range. So it picks up a lot of things that we see. But the visible range is in about a nanometer. So if you're talking about the visible, you've got a wavelength of, I think it's like about 4 to 7 nanometers. It's around that range. It's in the nanometer range. Nanometer, what's nanometer? Yeah, 10 to the power of negative 9. So a value of about, for instance, about 6 times 10 to the negative 9 meters would be something that we would be able to see, all right, a wavelength. Now you can work out the frequency of that wave easily, right, because you've got C is equal to frequency times wavelength. So you're going to have your wavelength is equal to 6 times 10 to the negative 9 times your frequency is equal to 3 times 10 to the 8. So your frequency will equal what? Not calculator. Come on, come on. Yeah, so the C divided by the wavelength, so it's going to be 3 divided by 6 is 0.17. Good. All right, because this when you divide it changes from a negative to a positive. And all right, so you're going to have that hertz. So about 5 times 10 to the 16 hertz is the frequency. Pretty quick, all right. You're looking at like a 10 million billion oscillations per second. So the electrons that cause this, the vibrating particles that cause this, were vibrating at every single second 10 million billion times. All right, and in the process sending out these little electric waves, electric fields, which are changed into magnetic fields, or changed into electric fields, and sends us off at 3 times 10 to the 8 meters per second. And we look at it here and we see, that's what we're seeing here. It's all coming in, all being from our eyes. So it's quite amazing, really. This is our electromagnetic spectrum. Now, unfortunately, you do need to have an idea where these things happen. You've got to have an idea where the wavelengths and the frequency of the visible light, where you get your X-rays, where you get your gamma rays, where you get your microwaves, where you get your radio waves. You've got to have an idea of where those are. You've got to actually learn that. You've got to have an idea for those numbers. Okay, so in the PowerPoint there's some stuff on that, I think. Yeah, so if we go, there's a PowerPoint which is on the website with some information on. It gives some of these values. Here it's giving us in hertz. So it's giving you, but you can work out the wavelength for each one of these. So radio and TV less than 10 to the 9. So you can work out the corresponding wavelengths for each of these. But you've got to have an idea of those wavelengths.